Okay, everybody. Good afternoon. Welcome to one more talk in the seminar series for the Institute for Software Research. I'm happy to introduce David Rosenblum. He has a very illustrious career. He did his PhD in Stanford. He spent a few years after that in Bell Labs, where all the good stuff was happening there. Then he came from Bell Labs directly here. He was a faculty here in our department at the time of Information and Computer Science. He actually left just a few months before I came, so we never were together here, unfortunately. But I know that his coming here feels almost like coming home for a lot of people who were here at the time. It's like, oh, okay, he's back. So after he was here, he tested the waters in startup land with a startup that did publish-subscribe networking. Very interesting piece of work. After that, he went to the University College of London. He went back to academia, was there for a few years, and now, to be even more exotic than Europe, he went to Asia, and he's now in the National University of Singapore, where he is directing the laboratory for Felicitous Computing. That he's going to tell us all about it. Now, David is a fellow for the ACM and the IEEE and has won career award, NSF Career Award, so he's a really, really good person to hear, and I'm looking forward to hear your talk.
Okay, thank you.
Yeah.
Hey, thank you very much for that introduction, Krista. And yes, it's very nice to be back here at Irvine. I really miss having worked here, really missed the time that I spent here. I was trying to remember actually when the last time was that I visited the campus, and I think the last time was probably in 2004 when Dick was general chair of the FSE conference in Newport Beach, and it's hard to believe it's been that long. And in fact, I barely recognize the place. This building wasn't here last time that I was here, so I got a little bit lost this morning when I was walking around campus before arriving at the building, but managed to find my way here. So, yes, as Krista mentioned, I've had a bit of a checkered history in terms of where I've worked and even which continents I've decided to work on. And as she mentioned, at one point during my career here at Irvine, I decided to take a leave of absence to work with a startup company called Precache that was trying to commercialize some technology in internet scale publish-subscribe communication. And the company was located in the New York area, but I still managed to live here in Orange County while I was working with the company. But like a lot of companies, a lot of startup companies in that era, the company eventually folded, and so I was looking for a new position. And then I made a permanent move to London, to University College London. And actually, I remember shortly after moving there, this woman from Texas that I know asked me where I lived, and I said, well, I live in London now. And she said, is that near New York City? And you know, this was, to me, it was just one of these, you know, typical stereotypes of ignorant Americans not knowing their geography, and it was all I could do not to laugh in her face. But then, a couple of years ago, I moved to Singapore, and Singapore is incredibly far from just about everything, and I started to think that maybe she had a more subtle point that I was missing at the time. Indeed, as you can see from this map, Singapore is very far from a lot of places. My wife is from Brazil, and this is probably about as far as you can get from Brazil anywhere in the world, and this was not by design. It just does make it very difficult for us to go visit her family. Now, on this particular map, you can't even see Singapore. Singapore is a kind of a small place. If you were to look at a map of it, though, it's, as you perhaps know, it's an island. It's a city-state, as it's sometimes called. Forget all of the cliches that you've heard about Singapore, about chewing gum and caning and those kinds of things. Singapore actually has a lot of similarities with Southern California. The weather is very nice all year long. Some people think it's a little bit too hot in Singapore, but it's warm every single day of the year. You don't have to worry about snow or cold weather or any of that stuff. Also, you know, there's not an excessive number of cultural opportunities that distract you from spending nice time outdoors or close to the waterside. There are some significant differences, though. Well, first of all, the beaches are much nicer here in Southern California than they are in Singapore. But Singapore is a fairly small place, and what I did here is I tried to make sure that I preserve the correct size of both Singapore and Southern California in drawing this map here. So if you were to overlay the island of Singapore on top of this map of Southern California, you would find that Singapore is about 1/3 the size of Orange County, and Orange County is one of the smaller counties in California. So one of the big differences here is just really the size of the place. Some people find it a little bit confining, but to me it's a reasonable size. Another way this size kind of becomes interesting is with respect to transport and traffic. So in Singapore, I don't even need a car. I wouldn't be able to afford one if I could, but I don't even need one because the public transport and the taxi system there is so extensive, it's so inexpensive, it's very effective. But you can drive from the western end of Singapore to the eastern end of Singapore in about 45 minutes, which would be, on this map, about the same distance from, say, Long Beach down to Mission Viejo. And my memory from living here is that you'd be hard-pressed to make that trip here in about 45 minutes' time. So we don't quite have the traffic problems in Singapore that you do here. So Singapore is a really great place to live, very modern, very livable. The university itself is a really great place. For those of you who pay attention to university rankings, you might have noticed that NUS, the institution I'm at, has been coming up in the rankings of late very rapidly. For example, in the U.S. News and World Report, of all places, we were ranked number 9 in the world in computer science. So it was very refreshing to see those kinds of rankings. And the university has been very good to me. When I first arrived, they gave me some seed money to start up a research institute in a topic of my choosing, and so I decided to build up a research institute in something that we're calling Felicitous Computing, which is the subject of this talk. And as the name suggests, there's an allusion there to ubiquitous computing. So for now, at least, you can think of this as being kind of next generation ubiquitous computing systems, but I'll define things a little bit more precisely as we go along. So indeed, the starting point then is this notion of ubiquitous computing, this notion that was first articulated by Mark Weiser in this very well-known article in Scientific American more than 2 decades ago now. And there's a lot of very nice things in that article that were very compelling and that resonated a lot with people who were looking for new paradigms for computing and new ways of solving a lot of problems in computing that just wouldn't seem to go away. And in fact, the very first sentence of the article really sets the stage very nicely. It says, "The most profound technologies are those that disappear." So that tells you a lot about what was being sought here in this original vision, at least, of ubiquitous computing. And if you read the opening paragraphs a little bit further, it talks about envisioning a world where computing is an integral but still invisible part of people's lives, and where the computers themselves vanish into the background so that they're completely unnoticeable. Now, in starting up this research institute, of course, we realized that this field of ubiquitous computing as an area of scholarly research activity is very mature now. There's been 2 decades of research, very nice research, and a very wide range of research results in many different areas, sensor networks, user interface design, software engineering, software systems design, a lot of very nice results, and certainly the research vision has to many extents, I would say, remained faithful to or consistent with the vision that was first articulated by Mark Weiser. And when people think about ubiquitous computing, they typically think of smart spaces of various kinds that are heavily embedded with sensors that can sense whatever's going on, sense what the current situation is, whatever it might be, so that the sensed situation then can inform some appropriate computational activity on behalf of various people. So, or it might be things like augmented reality displays, not virtual reality, but augmented reality, real reality that's been augmented with additional kinds of information feeds or whatever it might be. If you're wearing a pair of Google glasses, for example, and you're walking around and you want to know what it is that you're looking at, if you're touring Paris, for example, then having a sensor-rich kind of device that's mobile and could go around with you but which could be attached to you perhaps in an unobtrusive way, would give you would enrich your experience as you're living your daily life. Some people talk about smart highways, for example, cars going around in platoons, going down the highway in an autonomous fashion without drivers. I'm not sure I'm quite ready for that one yet. And of course, smart homes is another thing people have been thinking about. Of course, this is the Jetsons, so the idea of a smart home long predated Mark Weiser's article. But a lot of people have been working on the actual technology and applications to make this kind of thing a reality. So certainly the research vision has been very compelling. A lot of the research results are very nice. The question, though, is to what extent has the everyday user of computers actually started to benefit from this vision of ubiquitous computing? And I would argue that, and one of the real motivations for this research institute is that what the everyday user is experiencing is something quite different from what was originally envisioned by Mark Weiser. The reality in some ways is really kind of a nightmare version of what he was originally picturing, where you have people that obsessively are tied to their cell phones or other mobile devices, constantly caring and feeding for these things, keeping up with emails and text messages, or downloading the latest patches for the software systems that they're trying to run on their devices. And so far from fading into the background, these things are very much becoming an ever-present but thoroughly visible and thoroughly intrusive part of people's lives. Another aspect of the reality here is just what just doesn't really seem to be that there's much of a business opportunity here in ubiquitous computing, at least of yet. And the statistics that I'm going to show you on this slide are about a year old, so they're a little bit outdated, but they're probably not much different from the corresponding statistics from this year. So one interesting statistic then is that the average price of the top 50 paid applications, and these data are from the Google Android market, or Google Play as it's now called. The average price of the top 50 paid applications is just $3.79 US. Now, if this were, if we were talking about desktop software, we would think nothing about spending hundreds of dollars on a Microsoft Office package or Adobe Photoshop package or something like that. But when it comes to applications running on mobile devices, where the devices themselves are fairly rich with sensors and at least have the capability to do the kinds of things that were envisioned in the original vision of ubiquitous computing, people just simply aren't yet willing to spend good money on this stuff. And a good reason for that is that most of that stuff is junk. Okay, if you look at this application market, nearly 80% of paid applications have been downloaded less than 100 times. And we're talking about a platform here that's on phones of probably tens, if not hundreds of millions of people. Hundreds of millions of people are walking around with Android phones, and yet 80% of the applications in this application market have been downloaded less than 100 times. And which ones have been downloaded at least a reasonable number of times? Well, about 1/10 of 1% of these applications have been downloaded 50,000 times or more. So there's something here. There are probably various explanations you could give. The functionality of these applications just isn't very good. They're still very buggy. And like I say, people just aren't willing yet to pay good money for these kinds of things. And I guess, one final commentary about the reality of the situation is that stuff just does not work right. It does not work the way people should naturally expect that it would work. And I could give you dozens and dozens of examples to justify this. The example I'm showing you here is just based on my own personal experience with something that's very commonplace, very mundane. There's no, no interesting research problems underlying this, no interesting ubiquitous computing aspects to this, but it still kind of has some of the flavor of ubiquitous computing, and yet it probably involves the kind of frustrations that a lot of you experience on a daily basis trying to deal with applications like this. And what I'm showing you here then is problems in trying to synchronize my appointments calendar across multiple devices. So up until about 5 years ago or so, I had just one computer in the world. It was a laptop. I carried it around with me everywhere that I went. It had my whole life on it, my appointments calendar, my email, everything else was on this one device. And I didn't have to worry about any kind of synchronization issues. But then one day I got an iPad, another day I got an Android phone. Eventually I decided to stop schlepping this big laptop back and forth between home and work, so I decided to get a desktop machine at work. And so I was faced with this problem of how to synchronize my calendar across all of these different devices. And you would think, you know, here it is, 2013, you would think this problem would have been solved by now, but actually, at least in my own experience, it hasn't been. And it's just surprising how badly this actually works. So if you stay within a particular ecosystem, it turns out that it's reasonably, although not completely error-free, to do this kind of synchronization. So you can synchronize between the Mac and an iPad, or you can synchronize between Google Calendar and an Android phone. But as soon as you want to cross these two ecosystems, then that's where all trouble starts. And so the first idea I had was to sorry, it's telling me my battery is out. So the first idea I had was to make the copy on my Mac the master copy, and then push things out to Google, synchronize with the iPad. But what I found was that there were starting to get appointment conflicts on the iPad. Appointments just started being deleted in various places for no good reason. Even worse, some appointments were getting duplicated. And when I say duplicated, I mean not just an extra copy, but maybe a dozen extra copies of the same appointment appearing and polluting the calendar. And to top it off, there were issues with some firewall issues or security issues between these two worlds. And so this just wasn't working very well, and so I decided to try a different solution. And the different solution then was to make the Google Calendar copy the master copy of all of this, and then synchronize everything from there. This is working a little bit better, but it's still, you know, I'm still getting issues like conflicts on the iPad, and Google has its own peculiar ideas about what the right way is to treat time zone. So if you enter a time zone in Google Calendar, sometimes for whatever reason it just forgets what that time zone is and will convert it to an equivalent time zone somewhere else in the world. And so, you know, in one calendar it can say you have an appointment at such and such time in Singapore time, and a different calendar it can say it's in North American time. So I'm still not very satisfied with this, and I'm trying to figure out what to do. And so the next thing that I'm considering is just basically going back to the drawing board and just giving up on all of this highfalutin computer-based synchronization. But so it's these kinds of considerations, these observations, and these kinds of difficulties that people face in using computer systems that led to the formation of this institute. And kind of the key goal of this institute is to try to go back to what that original vision of ubiquitous computing was, to come up with really useful and powerful computer-based ways of enhancing people's lives, but to do it in such a way that the computers really do recede into the background, that they don't become these intrusive things that require constant care and feeding. So the hope here is that this is going to be a very multidisciplinary research institute involving people from many different faculties across NUS. We have collaborations going already, for example, with people in the School of Medicine at NUS. And the research that we're going to do also is very strongly driven by challenge problems from a number of different application domains. Most of the domains we've been looking at so far are multimedia and mHealth, and I'll say a few words later about some specific projects in those areas. But we would like to get into other areas as well where we think these kinds of ideas and this kind of technology could be useful, like public transport. So felicitous computing, what does this mean? It does turn out that this word is giving people a little bit of difficulty to deal with. But the basic idea here is simply what you would find in a typical dictionary definition of the word felicitous. And this one comes from the dictionary that's loaded here on my Mac. It says, well chosen or suited to the circumstances, pleasing and fortunate. Okay? So then felicitous computing is simply computing that is felicitous, computing that is not poorly chosen or ill-suited to the circumstances, computing that is not displeasing or unfortunate for the user. Okay? Now those of you who are somewhat steeped in ubiquitous computing probably are aware that one of the key elements of ubiquitous computing is context awareness, and so this particular definition is felicitously aligned with kind of the context-aware side of ubiquitous computing. But we also intend felicitous computing to be kind of an overarching philosophy of not just technology development, but also about the way that technology is evaluated and in terms of its impact on users. Okay? And unfortunately, I won't really be able to say very much about kind of the evaluation side, but I'll emphasize more of the technology side. So what are the key elements then of felicitous computing systems? Well, this is kind of very much very similar to what you would expect of a lot of software systems, including existing kinds of ubiquitous computing systems. So the notion of context awareness that I just mentioned, the idea that the applications that run on these mobile devices are going to be very strongly influenced by the context or the phenomena within the execution environment within which the applications operate. And these things might be, this kind of contextual information might be information that's local to the particular device, such as the battery level. This is a typical example that's used for local kinds of context information. Or it might be external context information, such as the current location of the device or the identities of the other devices within the neighborhood of the device of interest that might be discoverable through a Bluetooth interface. So context awareness certainly is a key element here. Also, intelligent, unobtrusive processing of the sensed context and the kinds of things that you do with the context. Sensing the context is just part of the problem. The context is typically represented in a very low-level fashion, and so many higher-level inferences have to be drawn about the context before you can do anything useful with it within an application. Another important element is robustness. Again, robustness is something that we in software engineering are always promoting. We are always talking about the importance of robustness, and usually when we try to define robustness, we say that it's graceful recovery from failure. But in this kind of environment, robustness needs to be much broader. It has to be more than just dealing with failure. It has to be, it requires dealing with unanticipated, yet completely reasonable, completely valid actions on the part of the user. So it has to go beyond, we have to go beyond thinking in terms strictly of failure and recovering from failure, but instead simply being able to deal with any kind of unexpected phenomena that might occur while a system is operating. And then finally, multimodal forms of interaction, I think, are going to be a very important way of helping these systems recede into the background and making these devices and applications less intrusive for users. And when I'm talking about multimodal interactions, I'm talking about going beyond the kind of traditional text and touch-oriented interfaces that are typically available, but using things like audio or voice or natural language processing as a way of interacting with systems, using gesture, for example. You know, tell me of a nice restaurant over here. Just being able to use your arm to do that rather than, you know, stand there for 5 minutes texting and searching and trying to get a connection with Google and all of that. Movement of the user is important information, as it turns out, as I'll show you later on. And even the emotion, the emotional state of the user could be an effective contextualized input for a lot of these different kinds of applications. So these are kind of a lot of technical characteristics, but ultimately the user is the important focus in these kinds of systems. And so the systems have to be designed in such a way that they meet a number of different criteria that would be important to the users. It has to be very natural to interact with the applications, and I would argue a lot of existing applications simply aren't that way. The system should be very useful to the users, should do useful things on behalf of the users. The kinds of things that we think about having these systems do should be realistic. They shouldn't necessarily be kind of space-age things that appeal to computer geeks, but instead should be things that really do realistic and useful things for people, and then ultimately should be beneficial to people rather than harmful to people. Okay, so we have a number of research directions being pursued in some of the different projects we have going on in this institute. Context awareness and context-aware adaptation are important threads there, and you'll see in the couple of projects that I'll be talking about the way some of this comes through. Multimodal interaction, we have some people in a media group at NUS that are very interested in this problem. We've just recently started a project on emotion sensing and emotion inference. This was a project that was inspired by some conversations we had with people in the Department of Psychological Medicine in the medical school in NUS, and they're interested in trying to be able to use mobile devices to sense the emotional state of their patients when the patients are not in a clinical setting, and then have those devices deliver some kind of therapeutic response to a heightened emotional state. So we're really at the very beginnings of that, and I'll say a few words at the end about some of the technical details behind that. And then certainly software engineering issues in mobile systems are an important research direction. So what I'll be doing for most of the rest of the talk then is to describe some work that we've done on a couple of projects. I'll describe two example projects in this area. One is really very much a software engineering project. This is a project actually that I started when I was at UCL with a PhD student I had there. This is a project on automated fault detection in context-aware adaptive applications. The second project really has very little, if anything, to do with software engineering. This is a more recent project that I did when I was after I arrived at NUS, and this is a project on context-aware mobile music recommendation. So I'll describe both of these projects in a little bit of detail. I'll show you some of the results that we got from these projects, and then I'll wrap up the talk. In both of these cases, it's kind of interesting. We did manage to solve some existing problems, some open problems in both system design as well as achieving robustness within systems. And then both of these projects, as you would always like to have in a research project, they did reveal some new and interesting research challenges. And I'll mention a few of those challenges at the very end of the talk. Okay, so this first project then that I'm going to talk about is this project on context-aware adaptive applications. And the basic idea here is that we wanted to come up with some approaches that could help us automatically identify the potential faults in the adaptation behavior of different applications running on mobile devices. And you'll see as we get through this what kinds of faults can arise and what some of the motivation for this work was. So as the name suggests, certainly one half of what these applications do is context aware. I already mentioned what the nature of context awareness is. The other half of the application then is the adaptation that happens within the application in response to any sensed or observed context changes. So, for an example, what I'm showing you here is just one very simple example of the kind of adaptation that might happen. Here we have a kind of a navigation application that displays to the user a high-resolution satellite image of wherever it is that they want to navigate. And if at some point the battery level on the device drops too low, below some threshold, then the application adapts its behavior to that new context and switches to a lower resolution and less power-hungry cartographic representation for the user. So it's just a very simple example of what we mean by an adaptive application, one that responds to context changes. Okay? So if you look under the covers of one of these context-aware adaptive applications, they pretty much have a very similar kind of architecture to them. They have to do similar kinds of things, irrespective of what the particular application is trying to do. Somehow or another, they have to be able to get a handle on what the actual real physical context is of the user and the device that the user is carrying around. Somehow or another, they have to acquire that context, represent it internally, process it, and then do useful things with it. Well, there are various ways of thinking about what that context is, and if you look inside the application stack, there's typically some kind of middleware that's available to do the necessary processing of the context information. And conceptually, at least, if not actually physically within a particular application, conceptually at least, you can think of there as being two parts to this middleware. The lower level is something we might call the context manager, the thing that's actually responsible for pulling that context information in and then providing some useful internal representation and a persistent internal representation so that that representation can be used for additional activities. And so what that context manager is doing then is acquiring essentially a sensed version of what the actual context is. It's not going to be 100% precise, perfect match because the context is continuously changing, but the sensors are just going to be able to periodically sample what the context is. Sitting on top of that context manager then is something we might think of as being an adaptation manager. It looks at that low-level context information and then somehow or another draws some inferences about what the context is in order to represent the context in a more abstract way, in a more useful way for the application itself. And then finally, within the application is going to take whatever context information that it needs and make some presumptions about what the current context is in order to figure out what the next step should be in its adaptive behavior. So there's really potentially 4 different levels of context at work here, and as suggested by the increasingly ragged appearance of those blue arrows, it's unavoidable that there's going to be information loss as you go through these different levels of processing within the context. And consequently, the view of the context or the view of the environment that the application has is going to be a fairly and rather imprecise view of what the actual physical context is, and that can potentially lead to application failures. Okay? Now, as it happens, the context manager in this middleware typically is implemented using a number of third-party libraries that typically are shipped with whatever hardware sensors are on board the device. And so there's typically very little coordination between the developers of these different libraries. They sense the context at different rates, and they have varying bugs and that sort of thing. So the third-party libraries are one potential source of faults in these systems. And then the adaptation manager, there's various different ways of constructing the adaptation aspects of one of these applications. But if you were to look at least at typical applications that you might download from an app store, a lot of these applications use some form of rule-based processing. It might be kind of a small rule engine inside with some declarative rules that are specified and given to the middleware. Or it might just be a bunch of if-then-else statements that says, if the location is home, then do this. If the location is office, do that. Somehow or another, though, in a lot of these applications, some kind of rule-based processing of the context is performed. And the rule engine actually is a source of potential faults as well. So what are the problems here? Well, with a rule engine and with any form of rule-based processing, what we have found is that even with just a very small number of rules, it's very easy to specify the rules in such a way that they embody a large number of different kinds of faults. The rules end up becoming very strongly interdependent with each other. And when I'm talking about a rule here, I'm talking about something that just has some kind of predicate describing the context of interest, and then some transition to a new state, and then some action that should be performed, some settings on the device, or whatever it might be appropriate for the particular application. But even with a small number, on the order of a dozen rules, these rules can become very complex and interdependent very quickly. And in the kinds of rule engines that we were working with in this project, we were working with rules that were specified at multiple priorities. So that adds an additional dimension of complexity where a rule at a higher priority may make it such that a rule at a lower priority never fires because the higher priority rule always comes into play. So it's very difficult to reason about adaptive behavior that when it's expressed in this kind of rule-based fashion. With the third-party libraries, the problem is a little bit different. So the libraries, these context sensing libraries aren't able typically to acquire a continuous stream of context information. Instead, they take periodic samples of the environment, and this sampling is done from multiple different sources. It might be from audio, it might be from GPS, it might be from motion, whatever it might be. But because of the way these libraries are constructed, it's quite often the case that the sampling is done at very different rates. And so what you wind up with is a situation where you have a high-frequency library feeding information very rapidly and a low-frequency library feeding information less rapidly. And there might be some temporary states of inconsistency where the lower frequency information still needs to catch up with the higher frequency information. Okay, so as I said, the goal here was to account for the fact that these context-aware adaptive applications have these potential problems inside of them, and then try to figure out some systematic way of identifying what the fault modes are in order to be able to help software developers, system engineers, cope with these things and try to help eliminate the faults. So the approach that we took is basically twofold. We start with the rules that we have describing the application, describing the adaptation behavior. And from those rules, we derive a particular kind of finite state machine representation, which we call an adaptation finite state machine. It's basically a simple finite state machine that's annotated with all the bits of information that we get from the rules that tell us what the state transitions are. The second step then is, once we have this finite state model, we essentially do kind of a customized model checking exercise on the finite state machine to fully explore the state space, fully explore the space of possible context settings in order to see which kinds of context settings are going to trigger which kinds of faults. And the algorithms that we developed for this state space exploration come in multiple flavors. Kind of the two key flavors are enumerative algorithms, which explicitly enumerate all the different possible context values in exploring the state space, and then symbolic algorithms, which use a binary decision diagram representation of the state space, and then do typical BDD kinds of manipulations that would be familiar to a model checking person. So I'm not going to describe the algorithms in detail, but I'm going to try to give you a little bit of a sense of what these algorithms are trying to do, and then I'll show you some of the results that we got with a very simple application. And one of the I guess I should mention also on the third point here at the bottom of the slide, the third step of the approach would be for the developer to actually confirm the existence of any faults that are identified by the approach. So the approach doesn't provide a way of actually localizing the fault or removing the fault. Instead, that would be up to the developer. And as, in case I don't, yeah, it does say on this slide, that what we're looking for here is potential faults. We have a finite state machine representation of what the adaptation behavior is. So any faults that we think we found are going to be potential faults. They may not actually manifest themselves in the running application because for whatever reason it might be physically or computationally impossible for them to do that. But in our experience at least, far and away the vast majority of these potential faults do seem to be feasible faults in the actual running application. Now, in order to do this work, we realized very quickly that we needed some kind of example of a context-aware adaptive application to help drive the research. And so actually the first thing we did before developing any of these approaches, before thinking about different kinds of fault classes, before doing any of the actual technical work, we just built an example application and started playing with it, just in order to see what kinds of faults that we would find in it. And the application we built is this thing we call phone adapter. It's a very simple kind of application, but also in many ways very representative of the kinds of things that you might expect an application running on a mobile device to do. And the basic idea here is that, you know, typically you have a smartphone and it comes with different modes on it. There might be a normal mode, a silent mode, a meeting mode, and each of these different modes has a different configuration of the settings of the ringtones and the vibration and the volume of the ringtones and some of these other things. And so what people always find, and what you typically find in meetings like this or in talks like this, is that people have forgotten to set their phone on the meeting mode, and so somebody's phone inevitably goes off because they forgot to turn on vibration, turn off the ringtones. So the idea of the application here is that instead of requiring the user to manually remember to do this stuff every time they change their particular situation, instead, why not just have an application do this for them automatically? It should be easy to do. And so the idea is that, you know, you might have these different kinds of modes or states or profiles that you want to have the phone set, and you want to have these selected automatically whenever you change your situation. So if you arrive at home, you don't want to disturb your family members, you want to put your phone on silent, and you want to turn the vibration on for whenever an incoming call happens. Or if you're in a meeting, you want to turn it on silent and divert any incoming calls to voicemail. Or, you know, if you're in a car, you want to divert incoming calls to a hands-free system and to turn the ringtones on loudly so you can hear the incoming call above the noise from the road. Well, it's a very simple kind of application, but one that potentially is very useful, and also one that can be done in an automated fashion using some very simple contextual information. And so the contextual information I'm showing you here is just simply GPS location, information that you can acquire through Bluetooth about other kinds of devices that might be in the environment, the meetings in the user's appointments calendar, and the time of day. With these 4 pieces of information, it's possible to write rules that allow an application to adapt from one of these profiles to another in an automated fashion. Okay? So for this particular application, we specified, I think it was something like 16 rules to describe the adaptive behavior, going from one mode to another or one state to another. And this is the finite state machine model that we derived from that set of rules. So each of the transitions, each of the arrows in this model essentially corresponds to one of those rules. And then the 9 different states there represent essentially the 9 different profiles that the application can set on the phone. So for example, up here in the top right, the arrow going from office to meeting is the activate meeting rule, and it has a particular predicate and action associated with it. And then the reverse arrow then is the deactivate meeting rule. So it's not a particularly complex state machine model, not a particularly large set of rules. There are also some global constraints that apply irrespective of what state the application is in, irrespective of what particular transition is being followed. Things like, if you want to be able to check the location through GPS, then first of all, GPS needs to be turned on the phone. Or locations are assumed to be mutually exclusive whenever they're specified in a rule. So if I describe something as being a home location, something as being an office location, those are assumed not to be the same location. So just very simple kinds of global constraints that have to be checked as well. Well, despite the seeming simplicity of this application and its adaptation rules, we even just immediately after we built it and started playing with it, we started noticing a number of very interesting and very strange kind of anomalous behaviors that could happen with this application. So one involved the home and office profiles. So the way this worked was if a rule wanted to determine whether or not the user was located at home, it would check the current GPS location. If the rule wanted to know if a user was in their office, it would look for a desktop PC in the environment of the or rather a laptop PC, or it would look for an office machine, basically, an office computer in the environment of the mobile phone, and it would detect that by looking through Bluetooth. Okay? So the problem here is, what if the user has a laptop at work and they decide to take their laptop home to work at home? Well, in that case, there's multiple rules that are enabled. You could either go to the home profile or to the office profile. The GPS for the home location is detected. The office laptop is detected by the device. So there's a non-deterministic choice here between which rule to fire and which adaptation to make. In this particular case, it's probably just a kind of a minor annoyance, right? It adapts to you go home and it adapts to the office mode, and your phone is ringing when it should be silent. Okay, so you apologize to your family members and you move on. This is just one of many possible examples of non-determinism, though. But you can also have faults that are more than just mere annoyances, but are potentially dangerous to the user as well. So here's an example where the user, for example, is sitting at home. They go outside, they get into their car, and they start driving down the road. Now, because the GPS sensor on the phone is sensing the location at a very high frequency, it notices the increased velocity due to the user being in the car and driving down the road. But the phone hasn't yet sensed the existence of the hands-free device within the car because the Bluetooth sensor is too slow. So instead what happens is eventually the phone, because it hasn't detected any Bluetooth hands-free device in the car, it adapts to the jogging profile rather than to the driving profile. And this is probably the last thing that you would want to happen, because the jogging profile just simply increases the volume on the ringtones without diverting the calls. It requires the user to answer their call. So if they're actually driving down the street and they have this incoming call and it's not going to the hands-free system, they're probably going to feel compelled to answer the call, even though it's dangerous, or even though they can, what is it, $195? I was seeing this sign on the highways here now about the ticket not being worth it. They'll probably still feel compelled to answer the phone. Of course, eventually the Bluetooth sensor does detect the hands-free system in the car, but by then it's too late to transition from the jogging profile to the driving profile because the developer didn't dream of this situation ever arising in there and never specified a rule to allow that adaptation to happen. So it's stuck in jogging mode until it can first go back into the outdoor mode. Okay? So this is just two of many, many examples of faults that we found. And after looking at some of these faults, we realized that they fall into a number of different classes. The first set of classes are things that we call behavioral faults. If you read the paper, you see a lot more description about these things, but I'll just try to hit the highlights here. Behavioral faults are faults that are essentially due to the intrinsic nature of the way the rules themselves are constructed. And a lot of these, probably the first four of these fault classes, are things that you might expect to find in any kind of finite state-based model of some system. Faults of non-determinism, multiple choices for how to transition out of the same state in the same condition, or dead rules, rules that can never fire, or states that can never be reached, or whatever it might be. The last two classes of faults, though, activation races and activation cycles, seem to be peculiar to this class of mobile, context-aware adaptive systems, because these kinds of faults arise due to the asynchronous way in which context information gets fed into the application. So an activation race then is a situation where the application is in a particular state, some context change happens that fires off a rule, the rule causes a transition to another state, and in that new state, the same context configuration causes yet another rule to trigger. So there could potentially be some arbitrary chain of rule firings off the same context value before the context eventually does change, or before you get to a state where there's no satisfied rule predicate. And this rule chaining can last some arbitrary amount of time until the context changes. So it might be completely indeterminate how long this chain of rule firings last before things become stable. So that's one set of fault classes. The other set then are things that we call hazards, and the name hazards here comes from the electrical engineering domain, and these are faults that arise because of the varying rates in which context inputs propagate through the circuit, if you will, or through the application logic. So these are faults that arise because of the varying refresh rates of the context sensors. Okay, so I'll just cut to the chase here and present some of the results that we found. These are results for both classes of algorithms, the enumerative algorithms and the symbolic algorithms. And both of these classes of algorithms are able to find the same set of faults. So what you're seeing here is that for each of the 9 different states in the phone adapter application, for the different kinds of behavioral faults, those are the number of distinct faults or distinct ways of triggering faults of that class that were discovered by the algorithms. And so you can see, especially for the classes of faults that are rather peculiar to these context-aware systems, the adaptation faults, there can be dozens or maybe even 100 possible ways of triggering these faults. And some of the even individual states seem to be particularly fault-prone, like the general state or the outdoor state. There was actually this sync state is the one unreachable state in this model. The sync state is the state where the application will automatically synchronize information in the background when nothing else is going on. And the reason it was unreachable is because it was the entry to that state was triggered by a rule that was specified at the lowest priority. So there was always some higher priority rule that would always dominate the rule that would transition to the sync state. So the sync state was never reachable. Okay, so these are the numbers for the behavioral faults. The numbers for the hazards are even a little bit more frightening in some ways. So that the column labeled paths there are the number of different adaptation paths through that finite state machine model that have to be explored in order to try to identify the potential for faults. So the numbers in the columns to the right then are the proportion of those numbers on the left that actually correspond to faults. So for example, 3,182 of the 14,000 paths in the general state, the paths out of the general state, can trigger priority hazard faults. So we're talking about really large numbers of faults, very fault-prone behavior here, again, with a very simple set of rules, embodying some very simple logic about adaptation between different states. Okay, so just to summarize this then, these rule-based context-aware adaptive applications can be extremely fault-prone, even for a very small set of rules. And you would probably be forgiven to think that, well, you should just abandon rules entirely and try to find some other way of doing this. And actually, as you'll see in the next application, we did apply another set of techniques to do this. The fault detection algorithms do find many actual faults. As I said, the vast majority of the faults that it finds as being potential faults turn out to be actual faults if you try to test them out. And the different kinds of algorithms we dealt with have different trade-offs, and I won't get into the different trade-offs here, but if you're interested in the technical details of the algorithms, you can go read the papers. Okay, so that was what I wanted to tell you about these context-aware adaptive applications. The next application I want to talk about is this context-aware mobile music recommendation system. And as I said, this in some ways, I guess this was inspired by the previous work. It shares many functional characteristics with that kind of activity-based profile setting application. And also, it tried to, in this project, we tried to find some alternative to using rule-based adaptation. As you'll see, we ended up using machine learning to do the actual adaptation. But apart from that relationship, this particular project didn't really have any real software engineering research content to it. That was pretty much a kind of a systems design activity. The basic motivation here, though, is that we wanted to find a way of automating the selection of music on behalf of users so that, again, they wouldn't have to shuffle down the street punching stuff into their MP3 player or their phone or whatever it was, so that whatever their particular activity was at the current time, there would be some appropriate piece of music that would be played to support that activity. And there's been research that shows at least that for short-term music needs that users have, their short-term needs are driven very much by whatever their current activity is. However, in order to solve this problem of doing fully automated music recommendation that's driven by activity, it's necessary to solve something that's quite often called the cold start problem in this particular field. And the cold start problem involves two kind of sub-problems. You have existing users, and you can perhaps potentially figure out what their music interests are, what kinds of things they play during different activities. But what if some new song gets released? How do you know what kind of activity that new song is going to be useful for? Well, that's half of the cold start problem. The other half then is, suppose some new user comes along and you don't know anything about their music preferences. How are you going to know what kind of music to recommend to them? If you can solve both of these problems simultaneously, then it's essentially a solution to the cold start problem. And one of the things we've done in this work is to provide a solution to that problem within this context of activity-based music recommendation. So you can think of this camera system, this context-aware mobile music recommendation system, as being kind of like a DJ sitting on your phone. It senses your current situation and figures out what a nice piece of music would be to play. And so you might be out jogging or walking the dog or studying or riding the subway or whatever it might be. But whatever the particular activity is, the application should choose a piece of music that's appropriate for that particular activity. So associating music with activity is half of what this application needs to do. The other half then is to actually infer what the current activity is. And for that, again, we do sensor-driven inference of activity. And we do this with just 3 bits of sensory information: audio, ambient noise information, movement that's sensed from an accelerometer, and the current time of day. And again, with just these 3 pieces of information, turns out to be fairly easy to, with fairly high precision, discriminate among 6 different activities. And the particular activities that we were looking at were running, walking, sleeping, working, studying, and shopping. Okay? So this sensor-driven activity inference is done in real time with those 3 different sensory inputs that I showed before. For the actual association of music with activity, we do that in an offline fashion. because essentially, at least for a baseline association, that can be done offline once, and then it can be tailored incrementally to a particular user's taste. So we do this kind of very low-level audio and acoustic feature analysis of music and identify which pieces of which kinds of music are appropriate for which activity. I have some data later on that I'll show you that demonstrates that it's actually feasible to do this, that music is not particularly a matter of personal taste, but there are apparently some low-level audio characteristics of music that are, if not universally, then at least kind of broadly suggestive of what kinds of activities a piece of music would or would not be suitable for. So the last thing this application does is it starts with a kind of a baseline recommendation configuration, and then it will personalize those recommendations or improve the recommendations over time as additional feedback is acquired from the user. So the alternative that we use to this kind of handcrafted, custom-built, rule-based adaptation specification was to use just off-the-shelf machine learning tools. So this was personally, this was my first entry into the use of machine learning. It was a very interesting and rewarding experience, and it certainly has its advantages and disadvantages in comparison with rules. One of the advantages, I guess, is that even though you know a machine learning model is going to be imprecise, you kind of know there's nothing you can do about it. So you just accept it as is, whereas with a set of rules, you realize, well, you know, if you write the rules in a particular way, you might be introducing bugs into them, so you need to improve the rules. Okay? So the particular kind of machine learning techniques that we used were supervised learning techniques. That is, we provided training data to build the models in the first place and then use test data to measure precision and other characteristics of the models that we built. And so the training data has to come from some representation of what the ground truth is. And so for the activity recognition, the ground truth was established by having a set of 10 users walk around, generating sensor streams of sensor data basically, and then periodically saying what their current activity was. And then for the music, what we did is we found this website, GrooveShark, where there's lots and lots of playlists of songs, and where people had actually gone to the trouble of saying, you know, I play this song when I'm jogging, I play that song when I'm studying. So there was a lot of already tagged data that we were able to mine in order to get this kind of first cut association between music and activity. And then the particular supervised learning techniques that we use employ incremental learning to incorporate those individual preferences as they're learned. So the architecture looks something like this. I won't dwell on the architecture diagram too much here. Basically, as I said, we do the processing of the music in an offline fashion, and the particular machine learning approach that we use is something called AdaBoost, and what it does is it builds separate classifiers for each of the different activities, and for a particular song it can assign a probability of that song being suitable for a particular activity. So this is done for each of the different activities, and that information is fed into a probabilistic model. And then for the actual real-time sensor processing, we do feature extraction from the sensor streams, those 3 different streams that I showed you. We feed that information into this probabilistic model. And this probabilistic model here in the center, the ACF, I don't even remember what that stands for. I would have to go back and check the paper. But basically, this is built around a naive Bayes model that combines the 2 pieces of information and then makes a recommendation of a piece of music for whatever the current activity is, delivers that music or starts it playing on the user's device, and the user has various ways that they can give feedback. They might quit playing the song after, say, 10 seconds just because it wasn't really suitable, and so the model will infer that the song was unsuitable for that particular activity for that particular user. Or the user might give an explicit indication on their device saying, no, I don't like this song for this activity. But somehow or another, feedback is given to the model, and the model then can incrementally incorporate that feedback without having to be completely rebuilt with all of the information. Okay, so several interesting results here that I want to show with you about this. First of all, as I mentioned, this is the data that I was mentioning before, showing that there is some statistically significant agreement among people about which kinds of music are appropriate for which kinds of activity. And so what we did is we we applied two different measures of inter-subject agreement on 10 subjects on what their music preferences were, and found statistically significant agreement for all 6 of the different activities. So what these numbers essentially represent is the percentage of agreement beyond just pure chance agreement, a pure random agreement on things. And you'll notice that with the kappa agreement statistic for running and sleeping in particular, the inter-subject agreement was very strong. I suppose that's probably because these are probably at the 2 extremes of the range of activities that we're considering. Running is probably the most vigorous and active activity, and then sleeping is, as you would expect, the least active activity, at least for most people. So we had 10 subjects basically manually tag a corpus of 1,200 songs, 1,200 of these Groove Shark songs that we had downloaded, and the p-value for all of these agreement values was less than 1/100th of 1%. So very high degree of statistical significance. Okay, the next thing we had to do was then figure out which particular machine learning approaches would be appropriate for this kind of application. Big problem for applying machine learning or any kind of computationally intensive approach on a mobile phone, of course, is that you have limited resources to do the computation. So there were a number of different candidates here, and again, what you're seeing is we had these 10 subjects do these different sessions of generating sensor data streams. So they did each of the 6 different activities. They did 30 minutes per session, gathered a ton of this sensor data, and then we fed all of the sensor data to 6 different machine learning algorithms, and then measured the precision and other characteristics of the models that were built. And while the naive Bayes model doesn't have the highest precision of any of these things, it has a number of important characteristics to it. It does support this incremental learning that can incorporate user feedback, and also it's something that can be very efficiently run on mobile phones, whereas some of the other algorithms would not work very well on a mobile phone in a kind of a mobile setting. So the naive Bayes seemed to provide the best trade-off between the precision and efficiency. Okay, this plot here shows the retrieval performance, the ability of the application to retrieve or to select appropriate pieces of music that the user actually agrees and are suitable for the particular activity. So the 2 curves at the bottom, the 2 straight lines at the bottom, the purple and the light blue, represent baseline cases where the recommendation is done in a purely random fashion. And then the 3 curves at the top show the selection using the machine learning. And what the graph is measuring here, so along the x-axis is a value of k, and what's going on here is that the application is recommending the top k songs for whatever the current activity is. So along the y-axis then is a measure of the precision at k. So given k top songs, what percentage of those songs are considered to be appropriate? What percentage of those songs does the user consider to be appropriate for the particular activity? So as you might expect, the higher the number k, the greater the number of inappropriate songs are going to start creeping in, but still these numbers show that the recommendation can be done in a way that exceeds purely random recommendation very well. Okay, so here's another plot showing the accuracy of the music recommendation. Here we have a 5-point Likert scale, and we're comparing three different modes of music recommendation. So R1, it says traditional. This would be a kind of a collaborative filtering based style of recommendation. The second the second mode, R2, this is the automatic mode of the camera application, where the application senses the activity automatically and then recommends a piece of music. And then the third mode is the manual mode. This is where the user switches off the activity inference and then just tells the application what the current activity is. So the p-values here show you that the two different modes of the camera application perform statistically significantly better than the traditional approach. But between them, between the auto mode and the manual mode, there really isn't much of a statistically significant difference between the ability of those things to recommend music accurately. And the Likert scale here is just the user's rating, the desirability of the particular recommendation. And then the final result is results involving this incremental adaptation, incorporating the user feedback. So the yellow bars represent the level of precision for the two different parts of it, the context inference and the recommendation. Before adaptation, and then the light blue bars represent the level of precision after the adaptation. For both of these situations, the precision does definitely increase, and particularly for the music recommendation, it increases quite significantly. And for this particular experiment, we had two subjects go around for 1 week, building up providing the feedback and incrementally improving the kinds of recommendations that the system was able to provide. Okay, so just to summarize this one, then this camera system is really, as far as we can tell, it's the first automated solution for short-term music listening needs that does provide a complete solution to this cold start problem that I was describing earlier. And instead of using this kind of handcrafted rule-based adaptation, instead it employs machine learning for a more robust form of adaptation. Okay, so those were the kind of the two main projects that I wanted to talk about. I'm going to say a couple of words about another project that we've started up very recently. I mentioned this earlier already. This is a project on emotion sensing. As I said, we have these colleagues in psychological medicine. We're very interested in finding ways of building applications that can run on mobile devices and that can sense the emotional state of users in order to be able to deliver some kind of, it could be very simple kind of therapeutic responses or even more complex kinds of therapeutic responses. And as it turns out, we just started this recently, and I didn't really know much about this area before starting this project, but it turns out that emotion sensing actually is a very active area of research. There's been a lot of research in this area going on already for probably a decade or more. A lot of that research is very good in the sense that it's been informed very strongly by theories of psychology and so forth. Part of the problem, though, is that a lot of people find that it's incredibly difficult to do this for a number of different reasons. And so over time, people have tried to find simpler ways of characterizing emotion and simplifying the problem a little bit. And what a lot of people who do work in this area do now is they try to find ways of classifying emotions along a very simple two-dimensional scale of arousal versus valence, as it's typically called. So valence just simply refers to emotion being either positive or negative, and arousal just simply refers to the kind of the level of arousal, the level of don't know how else to say it, arousal, high arousal or low arousal in the current emotional state. And even with this simple, crude, kind of coarse-grained two-dimensional characterization of emotions, it turns out it's still rather difficult to discriminate even between the four seemingly different situations shown up here. I put these pop references up here for kind of a cheap laugh, but if you dig a little deeper and just kind of think about it a little more, it's not even obvious that one of these, take an example, Jack Nicholson here in The Shining. I classified this as being a negative emotion, but he might feel very positive about the particular situation he was experiencing in that movie. So it's not at all obvious what, even when you observe somebody, it's not at all obvious typically what the right emotional characterization might be. But basically what we're trying to do here is to see if we can apply a range of multimodal sensors to try to help us do that, at least first cut emotional classification. And we're using a very wide variety of sensors that you can find on any kind of smartphone nowadays, a camera for looking at facial expressions, or a microphone for sensing speech, but also other kinds of sensors that are very easy to hook up to a mobile phone. So a galvanic skin response sensor for sensing skin conductivity, or pulse sensing, that sort of thing. perhaps by combining a lot of these different things and exploring the kind of the space of possible combinations, we can start to find ways of being able to do this better. And if we can exploit contextual information, whatever the user's current situation is, that's an additional piece of information that might give us better clues as to what the current emotional state is. But nevertheless, as I say, this is an area that's fraught with challenge. And in fact, as I mentioned earlier, one of the things these kinds of felicitous computing applications need to do is they need to do useful things to people, but do them in a way that doesn't cause harm, right? So if a person is going around and they're feeling happy and their application says, why the long face or something like that, it might trigger exactly the kind of emotional response that you were trying to prevent in the first place, and that the application thought existed, but it didn't really exist. So it might end up doing more harm than good to the user. So it's also a very sensitive kind of application area, one that's fraught with a lot of ethical issues. But even ethical issues aside, there's still a lot of technical difficulties underlying this particular area. One is just simply there's not a lot of agreement yet on what emotions really are. Are they is there some kind of biological signature for emotion, or are they just simply psychological phenomena? So there's a lot of psychologists think that emotions don't really exist in any kind of intrinsic fashion. They're just something that observers of somebody in some particular emotional state attribute to the person based on what they see. So there really, at least to date, there isn't much empirical evidence that there is some kind of biological signature of emotion. And we would probably need some biological signature in order to be able to sense it with sensors. There's also a very high degree of variability in the way emotions are experienced by individuals. So even, you have, from one day to another, you're in a good mood one day, you're in a bad mood another day, so you have these kind of long range emotional states that you're in. But even within a bad mood day, you might have brief moments of euphoria because of an email you got, or an email you didn't get, or whatever it might be. And these kinds of things complicate the picture very much. Different cultures, of course, are some cultures are ingrained to not display their emotions very lavishly, whereas other cultures do display their emotions very lavishly. They use their hands and they scream and they cry, even over very simple things. And even the same individual may experience emotions in very different ways in different situations. They may do incredibly loud belly laughs when they hear a joke, or they might just have a slight chuckle at some other joke, or maybe it's even the same joke and they just react to it in different ways at different times. So it's very difficult to figure out how to navigate this space. And if you think about this as being kind of an experimental problem to solve and requiring experimental approaches, well, this is where there's a lot of deficiency, I would say, in some of the work that's been done to date, because a lot of the experimental studies that have been done in emotion sensing use very artificial and contrived experimental settings where, for example, a subject is shown film clips repeatedly, and the film clips are meant to try to induce some emotional state. And you really have to ask yourself whether a user is actually going to ever be able to have a genuine emotion while watching a film clip. Well, it's probably not something that's really going to happen. So I see that I'm kind of running out of time here, so let me just try to wind up things rather quickly here. So basically the research agenda here is this multimodal sensing, trying to add context information, kind of situational information to the mix in order to try to improve the precision with which emotions can be sensed. We're currently building a computational platform that will allow us to collect sensor data and to do various kinds of processing with it. And then we are trying to think of trying to innovate more realistic empirical study design so that we can try to induce more genuine kinds of emotions. Okay, now I promised at the end of the talk here to try to say something about some of the remaining challenges that I see here. And of course I am here at the invitation of the Institute for Software Research, so it seems appropriate to kind of end on a software engineering note. So what I'll do here is just say a few words about what I see as some of the interesting software engineering challenges in these kinds of mobile ubiquitous computing systems. And I guess I think the best way to say it would be to quote Donald Rumsfeld. There's this very famous quote you probably know where he talked about known knowns and known unknowns and so on and so forth. And I think a big problem underlying many of these mobile and ubiquitous computing system is that they're just riddled with known unknowns. We know that there are things that we don't know about these systems, and we have to accept them. But the question is, what's the right way to go about doing things like testing a system? We have this camera system I showed you before. It embodies some machine learning models inside of it, and those machine learning models don't have 100% precision. We know that 1 out of 10 times, if the user is out jogging, 1 out of 10 times it's going to say the user is studying, right? That's wrong, but is that a bug? No, it's not a bug. It's just that it's the nature of the particular mechanism that was employed in the engineering of that particular system. So in areas of testing and validation and analysis and verification in particular, I think we really have to kind of rethink some of the ways that we characterize systems. Instead of just thinking in terms of pure binary, pass or fail of a test case, instead we need to really figure out what the right way is to go about testing these systems. And these kind of known unknowns, or this uncertainty, really arises in a number of different ways. There's the uncertainty in the way the execution environment changes. There's imprecision in the way that the context gets inferred, be it with rules or with machine learning models. Even different users or observers of a particular situation may disagree on what the right response of the application is. Even if it's just a matter of music recommendation. Yes, I like that music. No, I don't like that music. Same activity, same situation, right? And so for a tester, for example, how do you go about testing these systems? How do you know when something is a fault or a bug, and how do you know when it's just one of these things that has to be accepted as one of the intrinsic limitations of the application? So a good example of this might be Google Latitude, this application that helps you pinpoint what your current location is. So Google Latitude uses 3 different pieces of information to help you do that. It uses GPS-based location, triangulation from cell phone towers, and identification from Wi-Fi networks that it knows the location of. Now, if I pull my phone out now and ask Google Latitude what my location is, and it tells me I'm in Beijing, well, that's probably a bug, right? I'm certainly not in Beijing. I'm certainly not within the range of resolution of the 3 pieces of information that it should have available to it. But perhaps it's just a kind of a naive design fault on the part of the designer. Maybe there's none of those pieces of information in range within this room, and the designer just decided to show me what my last location was. Maybe I was in Beijing before coming here, and maybe that's just what the last location was, and that's all it's doing is telling me. Okay, well now what if I do the same experiment? I say, okay, what's my location? And instead of saying I'm here, it says I'm over in the ICS2 building. Is that a bug, or is that a feature? Well, it depends. It depends what piece of information it was using to make that inference. If it was using cell tower triangulation, then that might be a perfectly valid response. Even so, it might or might not be a valid response. If there's some fault in the application logic, it may actually have triggered the processing of that request may actually have triggered the fault, rather than it being attributable to the imprecision of the piece of information it was using to make that inference. So I think there's a really lot of nasty problems that are coming up here, where it's not going to be quite clear how to go about testing or understanding these systems. So 30 years ago, there was this very well-known paper by Elaine Y. Euchre called On Testing Non-Testable Programs, where she talked about a lot of the difficulty in being able to construct oracles for certain kinds of software systems. And I think we have a similar kind of situation here, similar in spirit at least, but it's very different from the kinds of systems she was talking about in that paper, which tended to be kind of numerical analysis kinds of systems and other sorts of systems like that. So it's not clear what the right approach here is, but perhaps what we need to do is employ some kind of relative notion of quality through comparison with other systems, rather than trying to come up with absolute quality assessment metrics where we say, yes, this passed, or it passed 75% of the test cases, or whatever it might be. So this is, at least within software engineering, this is kind of an area that I'm interested in exploring further. All right, so let me just try to quickly conclude here. So, this ubiquitous computing area that I've been talking about, and this notion of felicitous computing is rather mature now, I think. Certainly the technology basis for felicitous computing is here, but there's still a huge number of challenges that remain. part of the problem here is that we just simply lack a coherent and rich and systematic body of engineering principles to know how to go about designing these systems. And correspondingly, we also lack good means of doing evaluations of the systems that we do build. But the kinds of things we're trying to do at NUS are meant to try to realize that original vision of ubiquitous computing, where computers do become an integrated but yet also invisible part of people's lives. And so with that, I'll end the talk, and hopefully I have a little bit of time here for any questions that you might have. Jim?
It's really interesting. I think it provokes a lot of thought on like what we can do and what we can't do. Recently, there was a big controversy with somebody who their iPhone went off in the middle of a symphony. It was a quiet passage of the piece, and the thing went off, and it turns out that they had turned turned at the vibration setting, but they had also set an alarm to go off at that time. So the user had given it two conflicting instructions. Like this phone didn't know what to do, and the rules that it had was to go off.
Right.
And all of the discussion that happened at the time was kind of two camps. One was that the phone should have been smarter and kind of detected that these conflicting things, in this time of day, they're definitely awake, they're not sleeping probably, so it's not like they have to wake up for an important meeting or something. But the other side of this, the other kind of stance was that it should be dumber, in that no, vibration means vibration, just shut up and don't do any more smarts, just do this. I'm wondering if, and I guess all of your solutions here seem to tend towards let's get them smarter, which is not surprising coming from an academic. We all want to make things smarter. I wonder if there's a place though for the less smart solutions, like the paper calendar. Or
I suspect there are. I guess I would describe the situation. I would describe things a little bit differently. I guess in my view, users are never going to figure this stuff out right. I mean, it's hard enough for computer scientists to figure out, how to configure some application or another, or what the eventual behavior of an application is going to be in some situation. For the average user, they have not the slightest clue. They can't debug anything, much less even anticipate what's going to happen. And you see that manifest itself in so many ways. All these discussions that happen periodically every time Facebook changes its privacy policies. We're not even talking about bugs there. We're just talking about, how do I keep my information private enough so that people I don't want to see it won't see it, and people I do want to see it will see it. How do I do that? It defies the comprehension of a typical computer user to know how to figure out how to do that. So, if the user's not going to be able to do it, then all that's left is for the computer to do it. Either that, or perhaps the dumb solution then is kind of what I jokingly suggested doing earlier: give up the computer and just go to the paper-based solution. So, which is not to say I don't want to kind of promote this kind of utopian vision of computers doing everything for you. I'm definitely not a believer in that either. I think there needs to be a balance, but these systems are just way too complex for people to get their heads around, and it's not clear how to deal with that.
They thought going back to the phone adapter and trying it all over again, this time using machine learning and comparing it to the prior results?
No, I hadn't thought about that. It certainly would be something interesting to do. Yeah. I'm not sure that we ever took measurements of precision. It would be easy enough to do that with the old application, certainly. To just have 10 subjects walk around with it and
train it.
But also, at least for comparison purposes, then see what the precision of the rules is as well. It would be an interesting exercise to do that, I think. And it would be a very useful empirical comparison between machine learning and rule-based approaches, I think.
I have a question that you started to answer in your conclusions, I think. because when you transitioned between a pair of examples there, you said we tried a different approach, we tried a machine learning approach, but you were saying that wasn't a software engineering approach, or software engineering principles didn't apply because you couldn't like have analytic kinds of testing, I think. And I don't know, I want to like challenge you to think why just because you're using machine learning approach, there are still principles, there is still a software engineering concept. I don't know if you can comment on that.
And all I simply meant was that, you know, for example, in the music recommendation project, we used a machine learning model that had a precision of 90%.
Yeah.
Okay. Which means its precision is not 100%, which is what a tester kind of expects.
Yeah, I know. It's going to challenge your point of view. Yeah.
Okay, and
I think,
challenge it in what way?
Well, let me make a suggestion, and I don't know if this will work out because it's off the cuff, but I think in human-computer interaction, you work with principles all the time, and things aren't exactly going to be the same all the time. You know, there's a bunch of users who are going to behave a certain way, but not 100% of the time. So I think you might be able to come in your conclusions to start talking about what would be the principles. I think you can find them if you keep looking and look at other fields that deal with uncertainty.
Yeah, I suspect you're right. I just don't know what those principles are yet.
Yeah.
I mean, if I were a software tester of some industrial strength version of one of these applications that I described, or the music recommendation application, I'm not quite sure what principles I would apply to my test case selection, probably test case selection, but my testing activity in order to infer, is this piece of software ready to release or not? Okay, so one possible approach is to do what some people in reliability testing do. You sample the execution space a number of times. So do 10,000 executions, and if you get 90% precision from those 10,000 executions, then you can infer with some appropriate level of confidence that that the machine learning model is performing as advertised. If it's at 95% precision, even better. If it's at 80% precision, well, is there a bug in the system, or is it just the particular 10,000 samples that I had?
It's a challenge.
Yeah.
Okay, we'll take one last question.
You mentioned that complexity in devices is an impediment, an obstacle to felicitous computing. Couldn't it also be that everybody who makes devices right now has their own way of forcing the user to use them? For instance, I bought a TV and a Blu-ray player by the same maker. It's anything but obvious how these things work together. They manuals to go through, things to remember, and I don't think it has to be. And I can see where a device like yours could take all that off my back. If perhaps a standard were to be created along which manufacturers of electronic devices could be designed so they follow that standard, so that there is some harmony in interacting with them, in using them.
Yeah, I think this is a much harder problem than perhaps it appears it should be. A lot of these manufacturers, they do establish their own internal standards, at least. If you have a Sony TV and a Sony Blu-ray player, they speak certain protocols between them, and they're meant to be integrated into a single system. And to some extent, it probably works better than if you were to take a Sony TV and a Samsung Blu-ray player, whatever it might be. But yeah, it's...
Okay, so David is going to stay around for some more time. We have still some cookies left. Feel free to interact with David.
Thank you.